Hey guys, my name is Chris Rowe. My group members were Kendra Higgins and Chris Velasquez, and we're going to be trying to talk to you about the dynamics of a bicycle wheelie. So the objective of our project was to calculate the force necessary to lift the front tire of a bicycle to the desired position of 49.9 degrees, approximately 2.74 feet in the air. Looking specifically at the front axle, we calculated these values from real experimental data with several of the equations used in dynamics. Due to time and testing constraints as well as limited resources, we used a list of assumptions and approximations in order to perform our later spoken about calculations. So to discuss the background of our project, we mainly used theories and equations from chapters 11, 12, and 15. And the way that we were able to use these is through a tracking program, which the software is actually named Tracker. This tracking program allowed us to plot points on the rear axle and front axle of the bicycle and be able to plot these positions with respect to time, frame by frame, through each of our recordings. And the program even allowed us to average these different videos together, basically trying to make a unanimous value for these velocities, which basically rendered linear velocities. And from these calculations, we were later able to tabulate the angular velocity as well as angular acceleration. And from these tabulated values, we were able to calculate the forces applied by our rider, of course making an assumption at the pedals, which then allowed us to look at the forces that were applied at the handlebar. But of course, some of the other assumptions that we had to make is we neglected wind resistance. And like I just spoke on before, the rider exerted a minimum of his own body weight plus 50 pounds of force. And we assumed that the rider was able to maintain his center of gravity in the position that he shifted it to in order to move the bike with force that was calculated. And of course, you're not going to be able to apply this force all at 1 second. It's going to take a progressive amount of time, which is beyond our understanding. So we assumed that there was basically minimal to no response time in order for this force to be applied to the handlebar. For testing methodology, we recorded several slow motion videos of an unnamed stuntman doing a wheelie for approximately 8 feet. Our original projected distance was 15 feet, however, this was not possible due to the design of the Trek rental bicycle from the EGA library. Our rider was not able to continue applying force while in the wheelie. Instead, he was only able to apply force for a complete 1/2 rotation of the actual pedal. A lot of this reasoning can be seen inside of the large wheel diameter of 27 inches, which is a little over 2 feet, as well as a couple other things. The bicycle was designed in itself to be safe, so there would be no lawsuits for the university. Center of gravity is actually centered. In this slide, you can observe our unnamed stuntman performing one of our data collection runs in slow motion. We were at the top of the Ramsey deck over in ECV. So roughly right here is where the front tire is going to begin to pick up. As you can see, now as force is being applied by the rider, and then exactly one parking spot away, which is 8 feet, is where you have front wheel make contact again. On this slide, you can see the results from our tracker program, where the first graph is showing the position of the front axle in relationship to time, reaching the peak of the wheelie at 3.83 seconds after liftoff, then returning back to the ground approximately 4 seconds after reaching the peak. The other two graphs are showing position of the rear axle in relationship to time, as well as the relationship of the frame's position with respect to time. And on the right hand side of the slide, you can see some approximated and assumed values. Looking at calculations now, we were able to find that the transmitted force from the rider to the concrete through the rear tire was approximately 58.7 pounds. and the pull force from the rider onto the handlebars was 146.18 pounds. The net torque exerted on the rear axle from these two forces was 450.2 pound-feet. And from finding this net torque, we were able to calculate the angular acceleration, which was 2,084.7 radians per second squared. And then referring back to our tracker information, we were able to find the angular velocity to be 7,984.6 radians per second.
Bicycle, bicycle, bicycle. I want to ride my bicycle.